Hello, welcome back for this next lecture on refrigeration and air conditioning. In the last lecture, we have discussed simple VC vapor compression refrigeration cycle. In many textbooks, they have mentioned VCRS or VCC, vapor compression refrigeration cycle or vapor compression cycle. In that, we have discussed the four processes, the output of four processes, and the pH and TS diagram. So now we will today we will discuss how these processes or how these processes can be explained with the help of enthalpy. How we can calculate the exact heat addition, how we can calculate the amount of heat rejection, how we can calculate the net work done. So all these parameters we have to calculate by using the enthalpies. So for that purpose, just take the steady flow energy equation. So in this steady flow energy equation, so in this steady flow energy equation, the input is equal to output. What is the input? You are supplying the heat and the work put minus some that heat is using for the some amount of work produced. So that is your input, and the output is change in your enthalpy, change in kinetic energy, change in potential energy of a system. So here we are equating the steady flow energy equation with the help of first law of thermodynamics. So Q is the heat transmitted minus W is the work input is equal to, that can be improved in the enthalpy, change in enthalpy, that is delta H, change in kinetic energy delta Ke, change in potential energy delta Pe. Now we will apply this steady flow energy equation for each and every component. So for the refrigeration system there are four components are there. First one is compressor, second one is condenser, third one is throttling or expansion device, and fourth one is the evaporator, or in some case the refrigerator space. So first we will take the compressor. Now according to first law of thermodynamics, we are having the steady flow energy equation. Q minus W is equal to delta H plus delta Ke plus delta Pe. Now for the compressor, if we apply this, now for the compressor is a stationary, so there is no change in the kinetic energy of that compressor. Also there is no change in potential energy because it is at the same position. Kinetic energy formula is half mv square, potential energy formula is mgh. So the compressor is a stationary part, it will not move or it will not change its position, so the kinetic energy and potential energy is zero. Now the compression is the isentropic compression. Compressor in isentropic compression. Isentropic means what? Isentropic means reversible adiabatic. Now suppose if your process is adiabatic, now what we can do? So if the process is adiabatic, there is no heat transfer is there. So if your process is adiabatic, there is no heat transfer. So therefore you can write here if the process is isentropic, so therefore heat transfer during this process is 0. So put this all these value, Q is equal to 0, delta K is equal to 0, and delta P is equal to 0 in steady flow energy equation. So the equation becomes 0 minus W is equal to delta H plus 0 plus 0. Sorry. So the output of it minus W will be remain in the left hand side, and in the right hand side there is only delta H. But this change in delta H is limited for the process 1 to 2, because isentropic compression is only for the process 1 to 2. So here we are integrating with the help of within the limits 1 to 2. So therefore minus W is equal to integration of limits from 1 to 2. So there is change in enthalpy. So now we can back substitute the values of enthalpy. So H2 minus H1. So therefore work required W is equal to minus into bracket H2 minus H1. Now here the negative sign shows that work is consumed. Negative sign shows that work is consumed. Please remember this point, because the compressor will not produce the work. For running the compressor, we will provide the electricity, or we are providing the electricity to that compressor, and then only that compressor will start working. So for that purpose, the compressor is the work consuming device, and it is clear here. W is equal to minus H2 minus H1. So this is the formula to calculate the work done by the compressor during the isentropic compression process. Enthalpy at point number 2 minus enthalpy at point number 1. And always remember that this value is maybe minus, so that's why it indicates that the work is consumed by the compressor. Now this is the first case for the compressor, which can be compressor work consumed can be calculated as H2 minus H1. Now same steady flow energy equation can be applied to the second component, that is a condenser. So if there is a condenser, what the condenser? So condenser only is rejecting the heat. So in the condenser, the constant pressure heat rejection process is there. Constant pressure heat rejection process. So again, the condenser will not move, so therefore no kinetic energy. There is no change in potential energy. So delta Ke is equal to 0. Delta Pe is equal to 0. Now in the condenser is rejecting the heat. Condenser is rejecting the heat, so there will not be any production of consumption of work. The condenser is only rejecting the heat, so there is no issue of work produced or work consumed, because there is no any moving part. So therefore the work done during the process 2 to 3 is 0, but here heat is rejected, so therefore we are applying the steady flow energy equation for the process. Q minus W is equal to delta H plus delta Ke plus delta Pe. Now Q minus work done is 0, so Q minus 0 is equal to delta H plus 0 plus 0. So the equation becomes Q is equal to delta H. But this condensation process is limited for the process 2 to 3. So hence we are putting the limits 2 to 3. So Q is equal to limits from 2 to 3 into delta H. Integration of delta H from limits 2 to 3. So if we are substituting the limits, Q is equal to H3 minus H2. Q is equal to H3 minus H2. Now if we look at this diagram, H3 is less and H2 is more. So if you are taking the H3 minus H2, so the enthalpy can be negative. So therefore we have taken minus sign outside the bracket. So Q minus Q is equal to H2 minus H3. If the H3 is less, H2 is more. So if you are subtracting H3 from H2, H3 minus H2, the value will be negative. So therefore minus Q is equal to H2 minus H3. The value remains constant. Now, so minus Q is indicating that the heat is rejected by the system. Hope you have understood. In the previous case, there is minus W. So at that time you are saying that work is consumed. Here heat transfer is negative. Negative means what? Heat is rejected by the system. So negative sign showing that heat rejected by the system, and that amount of heat rejection can be calculated by H2 minus H3. Amount of heat rejected can be calculated by H2 minus H3. Now the third component, that is a expansion device. Third component is a expansion device. Now for the expansion device, again we are using the same formula. Q minus W is equal to delta H plus delta Ke plus delta Pe. Now for the expansion device, there is no any heat transfer is there, so therefore Q is equal to 0, because that is a very fast process. There is no time for transferring the heat, because as the expansion takes place, the pressure and temperature both are drastically reduced. So also there is a no moving part is there, so therefore work done is also equal to 0, and again potential energy and change in kinetic energy are both the terms are 0. So therefore if we are putting these values in the steady flow energy equation, so Q is 0 minus W again 0 is equal to delta H plus 0 plus delta Ke Pe is again 0. So the equation becomes 0 is equal to this process, 0 is equal to delta H, but this process is limited for the process 3 to 4. So therefore delta H from 3 to 4, delta H from 3 to 4. So you are integrating with delta H from limits 3 to 4. So if you are putting the limits, the value is H3 minus H4 and 0 is equal to H3 0 is equal to H4 minus H3. We are taking the upper limit. So if we are transferring this H3 to the another side, it becomes plus. So H3 is equal to H4. So in the expansion process, what you have observed, H3 is equal to H4, means there is a straight line is there in the pH chart. If you look at it, this pH diagram, H3 is equal to H4, there is a straight line, so which says that enthalpy is a constant. Enthalpy is a constant. So this process is also called it as a isoenthalpic process. Isoenthalpic process. Hope you have understood this point. First part, it is a compressor, in that the Q in that W is equal to H2 minus H1. So in that process you can call it as a work is consumed. If we are taking the condenser, Q is equal to H2 minus H3, so that you can say that the heat is rejected. And in the expansion device, H3 is equal to H4, means during the expansion process, enthalpy of the process stream can be constant. So that process is called it as a isoenthalpic process. Isoenthalpic process. Now if we take the fourth part, that is the evaporator. So in the evaporator, again if we are taking the evaporator, there is no any moving part is there in the evaporator, so work done is again 0. That evaporator does not move, so change in kinetic energy is 0. That evaporator is placed at the same height, so therefore change in potential energy is 0. So in that evaporator, what will happen? There is constant pressure heat addition process. Constant pressure heat addition process. So therefore Q is equal to Q minus work done is 0 is equal to delta H plus 0 plus 0. So therefore Q is equal to delta H. But this constant pressure heat addition process is limited for the process 4 to 1. For the process 4 to 1. So therefore we are putting the limit from 4 to 1. So therefore Q is equal to integration from 4 to 1 delta H, or integration of delta H from 4 to 1. So if we are putting these limits, Q is equal to H1 minus H4. Q is equal to H1 minus H4. So if you look at this formula, H1 is higher, H1 is lower, so the Q is always positive. Hence he can say that heat is absorbed. Please remember, please focus on the upper part, H2 minus H3, and here H1 minus H4. But that H2 minus H3 is when we are taking the Q as a minus. So there the value is negative, So that's why in the condenser we are saying that heat is rejected, and in the evaporator the value of Q is positive. So at that time we are saying that heat is absorbed. So these are the 4 points. On this basis you can solve the enthalpy problem. So if you are having the enthalpy of the system, so you can calculate the work done and heat transfer during the each process. So for the compressor, W is equal to H2 minus H1, and that process work is consumed. For the condenser, Q is equal to H2 minus H3, and during that process heat is rejected. In expansion process, the constant enthalpy is there, H3 is equal to H4, and that process is the isoenthalpic process. And in the evaporator, Q is equal to H1 minus H4, so which shows that during the process 4 to 1 heat is absorbed. So these are some basic phenomenon of the 4 components. Now if we have to calculate the COP of the system, how we can calculate the COP of the system? So if COP is the ratio of heat absorbed divided by work input, so the heat absorbed in the evaporator, or that can also be called it as a refrigeration effect, RE is equal to Q is equal to H1 minus H4. If some mass is given, so therefore total refrigeration effect is equal to QA is equal to MR into bracket H1 minus H4, where MR is the mass flow rate of a refrigerant. So if this is the heat absorbed during the evaporator, or it is also called it as a refrigeration effect, MR into H1 minus H4. Now again we have to calculate the work input. How we can calculate the work input? For that purpose first we have to calculate the heat rejected. So therefore QR is equal to, what is the heat rejected during the condenser, and during the condenser QR is equal to H2 minus H3. If mass flow rate is given, QR is equal to MR into bracket H2 minus H3. Now the work required for the compressor, as work input, so therefore W is equal to H2 minus H1, so therefore total work input is equal to MR into H2 minus H1. So please remember, if the mass flow rate is not given, you have to assume it as a 1, and if mass flow rate is given mass flow rate is given 1 kg per second, or 3 kg per second, 10 kg per second, 50 kg per minute, in different way that mass flow rate is given. So therefore that mass flow rate, that we have to multiply by that mass flow rate. Now the COP is equal to refrigeration effect upon work input. So therefore COP is equal to total refrigeration effect divided by total work input. So therefore COP is equal to total refrigeration effect is MR into H1 minus H4, and total work input is MR H2 minus H1. So we are taking the ratio MR into H1 minus H4 divided by MR into H2 minus H1. Both the quantities are in kilojoule per kg. So if you take the kilograms, if you are not taking it the mass flow rate, it will be in the kilojoule per kg, and if you are taken the mass flow rate in kilojoule per second, kg per second, at that time it will be in kilowatts. So my MR gets cancelled out. So COP of the system, if the COP of the system is H1 minus H4 divided by H2 minus H1. So COP don't have any specific unit, so it is the ratio of similar quantities. So COP is equal to H1 minus H4 divided by H2 minus H1. COP is equal to MR into H1 minus H4 divided by MR into H2 minus H1. In some cases, mass flow rate of refrigerant for the evaporator and the compressor is same, but in certain is same. So at that time you can directly use the formula COP is equal to H1 minus H4 divided by H2 minus H1, because mass flow rate is same. But if the mass flow rate for the evaporator and mass flow rate for the compressor is different, suppose some amount of mass flow rate is adjusted, so at that time you have to take the formula for COP is equal to MR into H1 minus H4 divided by MR into H2 minus H1. So similarly you can calculate the relative COP, the actual COP divided by theoretical COP. Actual COP can be calculated on directly on the system performance, and theoretical COP can be plotted by the pH chart. So these are the formulas for the calculation of the COP. So if in addition to this, if we are to calculate the piston displacement that we have discussed in the Bell-Coleman cycle, so again PV V1 is equal to MR, that is the mass flow rate of refrigerant, into specific volume. So that is the piston displacement of a compressor or volume of suction vapor. Also the actual volume, if the volumetric efficiency of the compressor is given, so at that time volumetric efficiency V1 is equal to MR into specific volume divided by volumetric efficiency. So in any way, if some changes can be given in the numerical, so that you can accommodate it. So volume is directly given, you can directly multiply by the specific volume to the mass flow rate. But if the efficiency is given by the compressor, then again you have to divide by the efficiency. Also the efficiency of volumetric efficiency of the compressor is also can be calculated as 1 minus C upon 100 into Rp raised to 1 upon gamma minus 1. So C is the clearance volume, Rp is the compression ratio or pressure ratio, and gamma is the compression index. If the process is adiabatic, it is 1.4. If the process is polytropic, it may be different. So these are the points on which we have discussed. In the next lecture we will discuss the different cases of the vapor compression refrigeration cycle.